right? So I think the journey starts. Let me minimize this. The journey starts even with very basic definition of what it means to do to count. Okay, to have numbers. What was number 4? So let me go back to our schedule. Okay, our schedule. And that is this picture here. So the first 2 or 3 lectures is about very basic definition of numbers, right? And what does number allow us to do? It allows us to, well, represent attributes. It allows us to compare the size of things. It allows us to set some variable, like a placeholder, to a value, and then change it later with the function and so forth, right? It allows us to do what's called Boolean logic, which is basically a true-false kind of thing. Okay, is 5 greater than 4? True. Is 5 greater than 4 and less than 6? Well, true also. Is 5 greater than 4 or less than 2? Okay. The second predicate, the second statement is false, but because you add it with the conjunctive or, okay, so only one thing has to be true. Well, 5 is less than 6, or 5 is less than 2. Well, it is less than 6, so it's already true. Okay, so regardless of the falsity of 5 being less than 2, the true statement, when you OR them together, becomes true. Okay, so it allows you to do very basic things like this. Okay. So the notion of counting, okay, the notion of taking stock of things, the notion of measuring the extent, the distance, the coordinate, the notion of adding things, the notion of subtracting things, all this is very elementary. It's something that you did very much in well, in a lot of cases in grade school, right? You know, when you were less than 10 years old. Okay. But we did cover them again with a more strenuous definition. Okay. What does it mean to be a number? What does it mean to be an integer? What does it mean to be negative number, real number, line, and so forth? So all this is important because not only will you get a better understanding of the whole ecosystem, so to speak, of mathematical objects, it allows you to be more precise in the future when the things that you want to analyze are not just numbers, but vector of attributes representing a country's socio-economic performance, maybe a vector representing your client, maybe a set of time series, maybe a set of social connection between a group of friends on the social media that you want to target. So all this ultimately is a lot more complex. And so you would need to do a lot of definition. Okay? So instead of saying a number is just a number, you have to say X is a number. It is a positive number only. It can only be positive number. Well, in the future, you have something like, this is a graph. It can only represent connection between people on a social network platform. And a second dimension would be their connection from a non-digital platform, like maybe there are cousins or something like that, okay? So this precise iteration or precise enumeration of what number is, what number means, is sort of like a discipline that would allow you to be more analytically precise and in fact more powerful. And the concept that I told you from, I think from day one, wasขี่ช้างจับตั๊กแตน. That means you're actually developing more tools than you need. Okay, so if I say something like 9x is equal to 72, right? You know right away x is equal to 8. But now I want to be more elaborate. I want to say I want to multiply 9x with something. such that it reduces the product to x. To do that, you have to find the inverse of 9. Okay, because by definition, inverse of 9, multiplicative inverse of 9 is something that multiplies 9 and gets you multiplicative identity, right? So what does that come to? Well, that's 1 over 9. Okay, you multiply 1 over 9 to 9x. The 1 over 9 and 9 cancel each other out, becomes multiplicative identity 1, and then you get your solution, x is equal to 8. So all this is very roundabout way of doing things. But again, it's more powerful because when that x, that 9, that 72 becomes something more complex, like a matrix, okay? Like system of something that, in the YouTube that I sent this morning, some of you may have seen it. It's a lot more complex. You need to do this kind of breakdown of individual steps, finding the inverse of the transformation and so forth. And this in turns translate into computational instruction that you would ask a coder to perform. Yeah. So like in the middle portion, focus on a particular mathematical object that we call vector and what we can do with them. Okay. What we can do with them. Again, because it's very powerful in its representation, its ability to represent not just a list of number, but coordinate in 2 dimensions, coordinate in 3-dimensional, okay? And of course, attribute space. That could be anything, like I said, socioeconomic performance of a country, behavioral profile of a client, or maybe measurements, physical measurement of your client that you want to make a tailor suit for. Inseam, the waistline, the height, the neck circumference, and so forth. All kind of things. These are represented by vectors. Okay, and the table of data that you see in Excel, that's basically just a list of row vectors. It's a list of row vectors. And then I did mention that, well, with this matrix algebra, what you can do is use it to represent system of equation. And then I introduce you to the notion. Well, I might as well use this. I think I do a little bit of a diagram for you guys there. Okay. So we have this thing of number, right? Okay. So let me just use it. Might as well. Okay. So number, counting. Okay, you get natural number. Measuring. Okay, you get positive real number like 1.5 meters, right? Once you start counting, well, again, what can our primate cousin do? Our primate cousin can do counting very well, but adding is a little bit challenging, okay? So now this is when human beings begin to outpace or outperform our primate friends, okay? So instead of counting 5 bananas and then 8 more bananas and counting to 13, you just count to 5, you count to 8, and you know how to add them. So that's adding, subtraction. Now, if you add 5 to 8, you get 13. But if you have 5 and you subtract 8, now all of a sudden you get to negative integer. Okay. Now you don't want to keep adding several times over if you can organize a large quantity into products. Okay. So multiplication becomes another game changer. Okay. Once you multiply, you no longer have to count 100 bananas. You can separate them into 5 equal size pile of bananas and count 20, right? And then you see that another one is also the same size, and there are 5 of them. So 5 times 20 is 100. So you're already more powerful, okay? Than baby or children who can just add, right? Now, once you multiply, the inverse of multiplication is division. Now, if you multiply a round number or integral number, you get integral number. But the other way around is not necessarily true, okay? And you know this because when you divide properties among friends or share a bill, you get, even though you have something that's integer, right? You went out for dinner and it's 100 baht, and there are 3 of you. So immediately you get something like 33.33333, whatever. Okay, so now you get rational number. Same with measuring. Measuring, you start with a notion of scale, and then we talk about this thing, which I told you that it's the simplest concept in life, but even seasoned or professional data scientists occasionally get confused between nominal scale, ordinal scale, interval, ratio scale. And then we're talking about, once we talk about the range of value the number can take on, we can talk about set, finite, countable, or countably infinite, bounded, semi-bounded, and unbounded. Yeah, so those are the words, so to speak, of mathematics. Those are the elements. Those are the very elementary words. But then you have to go to elementary sentences or mathematical statements. And here I show you in class 1, I think, the 2 kind of statements you tend to do in mathematics. First of all is you can think of relation like a phrase, okay, like a phrase. So equality, in this case, is it equal? Okay, so even though I say something like 5 is greater than 4, okay, and that's a statement. That's a statement. That's a relational statement. That's a statement that say 5 in relation to 4, 5 is bigger than 4. Okay, but we generalize this. We can go to falsehood. We can say is 5 greater than 4. Was 5 greater than 4? Is 5 greater than 4? Yes, it is true. But then you can start doing things like is 5 greater than 7? Then that gives you false, right? And then it allows you to do what's called Boolean functions, right? A relation B, A being 5, relationship being greater than, B being 4, 5 greater than 4 equal to true, 5 greater than 10 equal to false, right? So you can do this kind of binary check. Okay, so all of a sudden you have this kind of conditional checking, and this becomes something that will be the basis. And I kid you not, this is literally the basis of 90% of business decision making. It's checking condition. It's checking condition. Okay? Now, the rule can be more sophisticated, right? And the outcome can be very impactful. Okay, so after all this Boolean function, you end up with the decision like, yes, we will invest in this additional enterprise, or we will expand the franchise. Okay, but before you get to the decision to expand the franchise, it's actually Boolean logic. Okay, so I kid you not that all this thing, maybe not XOR, that's a little bit exotic, but certainly when you AND condition together or condition together. Okay, so I will invest in the expansion if, okay, if the market is expanding and we have the capacity, or never mind the capacity, never mind the market, or we have a synergistic partner that already has expanded market and capacity, or something like that. Okay, so it would be a lot more complicated. So at the end of the day, okay, at the end of the day, if you go, if you know, make this an exercise, if you like, you just pick up some business case studies, right, and see that they make kind of decision. Or some of you may be more exotic and look up military history. Okay, what happened at the final battle between at the Waterloo, for example, was the decision to bring the Prussian did this, and you know, why did they decide to have the battle there? The condition here and there, you go back to Alexander the Great, why did he use this terrain? Because it's blah blah blah, or Thermopylae, and why did the Greek decide to defend from the Persian in this area? Because it's narrow and it's edge. So there's a lot of if then, and or and or. Yeah. So just about every decision making comes down fundamentally to some form of Boolean logic. And the sophistication is, well, first of all, is you can add and or constraints or conditioning in a very complex way. if this and that, or this and that, and or this and this that, so forth. It can be very complicated. And also the conditions themselves can be based on some very advanced numerical calculation. Okay. But at the end of the day, all decision making just comes down to a human performing Boolean logic. Okay. As Boolean logic becomes more, not only it represents a human decision making, it is easily programmable, right, with a computer. So now the same way you can do human-like thinking, all right? If this and that, or this and that, but you can only keep maybe 3 or 4 conditions in your head. You can do the same thing in computer, except now you can check hundreds of conditions. By the way, this is the original, well, not original. This is what's called good old-fashioned AI, GOFAI. You know, there's it's actually a GOFAI, good old-fashioned AI. Yeah, it's called symbolic AI. It's a little bit like that. You know, it's checking if and then, except you have computer do the if and then. Now, the AI that you have in your iPhone is based on very different approach to capturing human intelligence. But you know, this is not the place to go into that. Okay. By the way, next week I have to give an introduction to the applied digital intelligence track. So it's meant for, well, it's also for you guys. It's meant for especially for first year, I think, students who are beginning to have a firm idea of what they want out of Bahasa education, and they want to specialize in this track or that track and so forth. So we have 4 lectures, one on the sustainability track, one on the smart cities and so forth, one on the healthcare and modern healthcare, and the other one, the last one being the applied digital intelligence. Okay, so I would go over some of that concept. But anyway, so just all you need to know is that something very simple that we did, you know, is it's 5 is greater than 4. 5 is greater than 4, or 5 greater than 10. Okay, like this. It's true, right? Well, it's not all true. It's only true here, but because you have this thing, which is or, you can say, let me write it this way, or 5 greater than 4, 5 greater than 10. Okay. Oops. Okay, so it's true. The same thing. So this is a shorthand for and or. This is the function or this or that. Okay. And when I told you about the complexity, you can do this as well. And 7 greater than 11, 13, whatever. Then it's false because this or this is true, but and this is false. So now this becomes the basis of what's called like decision tree. Okay, we learn about that later, maybe in business management. Yeah, right. Okay, so that's relation. You turn relation into what? You turn it into operation. Well, we might as well talk about operation in the general form. And of course, mathematics from grade school. You have add, subtract, right? Now, in this case, I make the distinction between equality as a statement or as an assertion, whether or not A is equal to B, to something like this, which is an assignment. When I say A is equal to B, it has to be true because I make an assignment. A has to be equal to B. Okay. And then you have the concept of inverse, and they have the concept of function. This is more general, complex strings of combination of this, okay? And then the notion of what? Independent, dependent variable. Remember that? So independent variable would be something like x, right? Okay, f of x is equal to a x plus b, for example, right? Now, so this, when I do this, x is free to be whatever it is. Yeah, so it's independent variable. This is a function. This function produces another variable, but that variable depends on the first variable. So it's not independent, it is dependent. Yeah. Now this function, what does it do? It multiplies x by a and add b. Now this a and b is like a variable, but at this instant it is fixed. In this case, a is always equal to 5 and b is equal to 7. Okay. And then in another circumstance, you change this value. So the constant, okay, that can change its value. So it's sort of like a halfway between variable and a constant, right? It's called parameter. Yeah, parameter. Okay, so that's basically the very elemental thing that we went through. Again, the idea here is that it's very elementary, it's very basic. It's something that you could get the answer right, 100% of the time because you did this in grade school. But now you understand more complicated, a more powerful way of thinking about it. So you're now able to think of mathematics as tools, as tool for design, as tool for optimization, as tool for decision making. And then again, we move to the middle portion of the class, okay, where I started to go into linear algebra, but very simple, no theory about how to do things, advanced calculation. But first of all, the notion of algebra, again, it's this word is related to the word algorithm, which again is named after the Arabic mathematician way back hundreds of, over 1,000 years ago. Okay, the idea here is that we have something that's x. Okay, x is something. You can shrink it, you can expand it by multiplying it to some kind of scaling factor, a. Okay. You can also perform some operation to another member, like this is a binary operation. The point is that x itself, x multiplied by a, and x plus y or x minus y, say, still belong to the same space that x roams in. So if x roams in two-dimensional space, like a vector, two-dimensional vector, right? Ax is a two-dimensional vector, right? And if x is two-dimensional vector and y is two-dimensional vector, you can add them and you get z or z, which is also a two-dimensional vector. And the quick example you can think of is that x is a two-dimensional vector consisting of north-south and then east-west distance. So that's your coordinate in 2D, right? So x is what you travel in the morning, y is what you travel in the afternoon, x plus y is equal to your travel for the whole day, right? That's it, that's it. And at the end of the day, it's all coordinates. It's all coordinates. Now I introduce you to something more interesting, which is concept of linear transformation. Yeah? Linear transformation, which will be represented in our class, in our case, by the middle portion of the class, right, would be performed using what's called matrix multiplication. The mechanic of it, you just learn from, dot product. We show you how that's done. But the essence of linear transformation is quite simple. If you perform transformation of something x, and that x has been scaled first by factor a, it's the same thing as performing that transformation and then scale it later. So it doesn't matter. You can scale it first, perform the transformation, or you can do the transformation and then scale it. Okay, so remember the example, L could be something like a weight loss matrix. Remember I told you guys about that? Like take a transformation of the person's weight and waist size, something like that, right? Now, if a person, another person, Y, is 10% heavier and 10% wider at the waist, and you perform the same matrix, weight loss matrix, it's the same thing. The result will be the same thing as applying the weight loss matrix to the original person who is X, and then scaling everything up by a factor of 10%. And also, okay, also you can do this in this sense as well. Linear transformation of sum is equal to sum of linear transformation. But of course, this is abstract. What I really mean, or what I really show you how to do, is matrix multiplication, right? Matrix multiplication. Now, matrix multiplication is when you multiply a vector by a matrix. Now, the good. I think I sent you a video for very good visualization. If you think of x as an arrow from 0 to x1 and x2, some kind of coordinate in 2 dimensions, when you multiply by a 2 by 2 matrix, you're doing two things. You kind of like lengthening or shrinking the size of the arrow, and you're also rotating. You're doing both. You're doing both. You're doing both. Okay? So you can think of it as a moving operation, but we don't call it moving operation. We call it linear transformation. Now, we didn't have time to go over this, but I just want to mention. Something. Yeah. If let me go to Mathematica. Yeah. Now, AX. Okay. So x is a vector, right? X is a vector. Okay. And then A is equal to A, B, C, D. Okay. And then Y is equal to A dot X. Okay. So you get this. So the first element of this, the second element of this. So again, this is a coordinate. This is another coordinate. And if we think about it, we can do this. So this is X and this is Y. So not only is it changing the size, in this case, getting bigger, it's also rotating and stretching, right? Now, the point is this. It turns out that for this matrix, yeah, if you take this, you turn it to here. If you take this, you turn it to here. But it turns out that there's one natural direction. Yeah, let's just make an artificial case. Let's say there's a vector x here that when you multiply by a matrix, it does not rotate. This is a special case. It does not rotate. It can only go to here, ax, okay, or it can make it shorter, or it can make it go the other way, negative. Okay, so it can make it longer, it can make it shorter, it can flip the direction, but it does not rotate. It doesn't do this. This means that the result of the transformation result in the same direction. Same direction. Now, you can say that going the opposite is not the same direction. Well, mathematically, it's the same. It's just a negative. Okay. So by same, it means that it's the same angle. Okay. The German word for same is eigen. The German word for same is eigen. So if you can find some kind of special direction, V, such that A dot B is equal to not the matrix version, but some kind of scalar. Scalar multiplication. Okay? This is one of the most powerful tools in mathematics. It's called eigensystem. This is the matrix. This is called eigenvector. This is eigenvector, and this is eigenvalue. It's saying that, okay, if you think of A as some kind of transformation, so this would be something that keeps the proportionality. Yeah, keeps proportionality, because even though you're transforming, okay, you are allowed to get the ratio between x1 and x2 to be different. If you don't have x1 and x2, you have v1 and v2. You select it such that when you multiply by the matrix A, all you're doing is stretching or shrinking or reversing. And this is called eigensystem. This you would learn in year 1, because this is going to be very powerful. Okay, it's sort of like finding a sweet direction. Okay, it's finding the groove. You know, let's say you want to study medicine, right? And then you watch documentary videos, and you become inspired to become a musician. Okay, you change your mind to become a musician, and you watch more documentary video, and then you change your mind, and now you want to be a physicist. You know, your direction is changing. Okay, and so every time you watch documentary video, you change your inspiration, your direction. But let's say you found your true calling, and your true calling is to be an architect. Okay, and you are an architect, and you watch you know, inspiration document, doesn't matter, biology, physics, news, politics, everything. Every time you go and watch a documentary, you come back and you just want to be an architect. Okay, you just keep wanting to be an architect. Maybe you want to study more, you study less. Okay, but it's still, you want to be an architect. It's that direction. You see everything in your world from an architectural point of view. It's that kind of groove. So eigensystem is sort of like a mathematical way of saying, when you find that V is the direction, like you're in the groove now, you set in the groove, you're not going anywhere, you're just on this road. Okay, you're not turning left, you're not turning right, you're on this road. Or you are backtracking, but you're on that road, you're not changing the road. Okay. That's and now last class and last 2 classes, we talked about getting you to calculus, and calculus deals with 2 things. It's very simple, right? It's very simple. It deals with rate of change. Rate of change. Okay. And that rate of change can be speed, because it's the rate of change of the location or distance travel. Okay. It can be rate of change of profit, amount of money in your bank. Okay. Deals with rate of change. The flip side of the rate of change is that, you know, instead of finding the rate of change, and you want to find it in an instantaneous way, okay, not an average. We could do average rate of change for millennials, okay, but until Newton and Leibniz came along, do instantaneous rate of change. The flip side of rate of change is cumulative change. If I give you a history of speed and a starting point, you can actually determine at the end of the day, if I give you, you know, millisecond by millisecond account of where the speedometer reads, and I tell you, you start at Sanam Luang, okay, and you go on a straight road. Okay, I give you a millisecond by millisecond account of a speed from 0 up to 30 miles an hour, 40 miles an hour, maybe back down to 0. Okay, you can actually integrate all the incremental movement of your car and get a total distance. So this is sort of like a flip side of one another. And when you go to calculus class, this will be called the fundamental theorem of calculus, the first fundamental theorem of calculus. Okay, it's the link between differential calculus and integral calculus. Okay, now the beautiful thing that I left you with last time was this. When I talk about system of linear equation, we spend a bit of time dealing with 3 situations. Okay, can A sort of like is A equivalent to 0? Okay, and we call that determinant. Well, the technical word is called invertible and singular, but never mind. There are 2 situations. One situation corresponds to There's a unique solution, right? There's a unique solution. How do you find that? How do you find that? You find that by find inverse of A and left multiply AX, and then you get AX. So that's your unique solution. Now, also, there's another situation. There are two situations where you have infinitely many solutions and you have infeasible or no solution. Okay. And I mentioned that in matrix algebra class or in grade school algebra, you always see this because the teacher made sure the number came out this way. Okay. Occasionally you see this, but you never see that. Now, I mentioned to you that in life, you never run into this situation. You rarely ever run into this unique solution, or at least you will not be paid professionally to solve it. Because if the solution is unique, there is no decision making. There are only two situations that you are likely to run into in your professional life. That is infinite solution or no solution. Infinite or at least multiple. Okay, multiple solutions. Okay, now this is sort of like a business decision making. Decide amongst the solution S, which is best. Okay, decide, and that's called optimization. Okay, now if you have no solution, you have to sort of like find your way around, and that's basically two things, right? You go to the engineer to engineer a solution. Okay, or you are inventor, innovator, inventor to invent a new solution. Okay. By the way, once you have the invention, what happened? Invention plus, a whole bunch of strategic stuff. Plus luck, plus good, not only luck, but also the right time. Okay, is equal to right place. Is equal to innovation. Now, when you invent, the engine here is technology. So this is where technology comes from many areas. Okay. So this is basically definition of Mathsci, right? You're learning to be innovative by using transdisciplinary. But even if you're doing this, once you did this, that's not the end of your job. Once you did this, you will make the problem feasible. Once you did this, if you did this right, if the engineer did their job, if the inventor did their job, you will make the problem feasible. And once again, you will go back to this optimization. Okay, so you invent some gadget, you still have to optimize that gadget in terms of the setting, the configuration, the modality of dealing with the clients of the platform. Because now you have a solution, you have a way to do things, you have the way to deliver healthcare, you have the way to address sustainability challenges, you have a solution that would solve traffic problem in smart cities. But just because you have solution, you're not going to get one solution now. You're going to get infinitely or multiplicity of solutions that has to be optimized. So you will never get around to optimization in life, I can tell you this. Now, the nice thing, and I use this as a segue, was because the optimization is not done by choosing the best by choosing the best. I think there's a construction or something somewhere. So choosing the best, okay, has to do with differential calculus. Why? Why is optimization? Because optimization, choosing the best, right? Optimization is choosing the best. Okay, choosing the best means the improvement function, i.e., make better, making things. Okay. Improvement function cannot improve further. So what does that mean? It means that improvement function has zero slope. Well, what's a zero slope? It means derivative calculus is equal to zero. Okay, so that's why, okay, that's basically why in life, I maintain that you are going to be employing these two very powerful of analytics. Now, one is linear algebra, one is calculus. Now, this has already been performed or created like a sort of like a recipe. There's a lot of good recipe in linear algebra. There's a lot of good recipe in calculus. And there's a lot of good recipe that would apply linear algebra and calculus to real life data. And people have done this for 50, for 100 years. Okay? And what they end up with are models, mathematical models. So combination, bunch of all this together create what's called a model. And some of you, especially those who are going into the applied digital intelligence tracks, will be focused quite a lot. I wouldn't say exclusively, but let's say more than 50% of your time on the type of model called machine learning. Or some of you will be more focused on a more general framework called artificial intelligence. So artificial intelligence and machine learning, you can think of it as a big elaborate engine. But when you open the hood, you look down at what the engine is made of, it's made of algebra and calculus. Now, it would be non-linear algebra. Okay? It would have non-linearity. It won't be just linear. Okay? Because after all, if it's linear, then calculus, instantaneous speed is the same thing as average speed. So it would be non-linear. But again, you use a lot of linear algebra because you have this vector. So essentially from here, you get the notion of vector and how you manipulate it. From here, you get the notion of change and how you can account for change. You can account for total amount of cumulative changes and so forth. Once you have all this, and mathematicians, data scientists over the past 100 years have been using this to cook up very elaborate recipe. And those recipes are called models, or if you implement it on a computer in steps, it's called algorithm. So all this will go into the algorithm. You sometimes you hear words like a YouTube algorithm, right? Well, YouTube algorithm, what does it do? YouTube algorithm, yeah, that's a good question. What does YouTube algorithm do? Okay, what does YouTube algorithm do? Okay. YouTube algorithm, okay, what does it do? Okay, it checks. A, you have lots of view, okay, and B, types of viewer, okay, and based on this, it does a whole bunch of if, then, and, or, it's a little bit like Boolean logic. Then If the result is equal to true, then YouTube shows your video to, say, particular profile of viewer and or give you money. Okay, so YouTube algorithm basically is a computation in step, but the computation basically is going to do fundamentally something similar to Boolean logic, and it's going to use a whole bunch of things that we talk about. Okay, so anyway, so that's sort of like a wrap up of where we are. So this is going to give you a preparation for what comes next, which to you then is a proper linear algebra course and elementary calculus. Now, I kind of sympathize with Chris, who's Chris, by the way, is our new recruit, right, in the gifted faculty. This will actually be his first lecture, so he's very young. He just graduated. So what he's going to do is going to take you through linear algebra, elementary calculus, and maybe a little bit of probability and statistics. So he has a lot of ground to cover. So hopefully that he does not have to give you any more intuition. Okay. So we talk about this thing about system of equation and so forth. Okay. So this by the way is I'm going to give this to Chris. Whether or not he uses this or he uses a more traditional textbook, that's up to him. Okay. But again, this is the concept of matrix algebra. In this case, 2x2 matrix as a system of equation. Right? So now you get unique solution. Okay. But if I somehow make this, yeah, imagine it's parallel, so you don't get solution. And if I move things, so I can move this thing around to see whether or not you get a unique solution, infinitely many solutions, and so forth. Okay, so that's basically it. That's basically what we have done. Now, what I want to show you a little bit here is now what it means to do interactive mathematics. Yeah. Again, this is the concept of using Mathematica. It's a concept of Mathematica, using Mathematica as interactive visualization and computation. Okay. So I'll give you a very quick example. Okay. Quick example. And in fact, the TA has already given, has already prepared for you some example as well. But the notion here is this. The notion here is that instead of, if you open a textbook, let's say, or a typical textbook, right? What you would see, hold on, let me move this thing here. So that's the block. In a typical textbook, you have the concept of whatever it is: marketing, economics, finance, engineering problem. You have equations, you have numbers, you have text description, and then the result of that computation will be some kind of graph, okay, some kind of plot. Y is a function of x, y is a function of x1 and x2, and so forth. And then you would have picture of those graphs. The concept of interactive mathematics, yeah, in this case, has two values that we will use in Basai. One, as an interactive pedagogical tool. Pedagogical means, has to do with teaching and the system of making curriculum and so forth. Instead of having just one picture like this, okay, I can have many pictures, and those pictures changes according to different parameters. So instead of having one figure to represent a concept, you can have, infinitely many, or you can have multiple pictures. So in this case, for example, I have a picture. You don't have to pay attention to what this represents, okay? You don't have to. Just notice that there's some kind of matrix here. There's some kind of vector here. There's some kind of matrix multiplied to a vector. I'll show you here. Let's make it bigger. Matrix multiplied by a vector, okay? Now, in this case, you actually left multiply by a row vector again, and you get something that is dimension 1 by 2 times 2 by 2 times 2 by 1. You actually get a scalar back. You get a number, and you can take a square root of that number, and you get some number. Okay? It doesn't matter, but all you have to know is that it involves matrix algebra in here. Okay, matrix algebra in here, and then square root function. And this is some kind of graph. This is some kind of you know, in finance. Let's say I actually literally use this to teach an online seminar for I think it was organized by the Thai Bond Market Association, people who professional who traded bonds and perform investment management, asset management. Okay. Now, the idea here is that instead of having this, you may not have the right. You may want some more intuition. Okay, this depends on parameter. Okay, this is a particular example of a market of two assets. It has certain correlation. Now, if I want to have more intuition, what if the two assets are positively correlated? Okay, what if I want to do that, right? I can just move this. I can just move this. Sorry, for some reason. Okay. Oops, sorry. Oh, I haven't run this worksheet. Sorry. Okay, so the reason it didn't run was because well, it hasn't run. So this was picture from taken from when I closed the program last. Okay, so it hasn't run. For some reason, this is taking longer than I thought. But anyway, so I can change all the parameters. Okay, so this would be pedagogical tools. So any kind of concept, whether or not it's machine learning that you will see into applied digital intelligence, or you can say, well, maybe some kind of graph that has to do with the healthcare effectiveness of a policy, right? And the things that you want to manipulate would be different assumption. Okay, so let's say that in your healthcare project, you're dealing with some kind of system of delivering community health care, and you have some kind of function, and that function depends on assumption like the rate of aging or something like that, or population growth or something. And you want to say, well, I don't want to do this just for one city in Thailand. I want to do it for any city in Thailand, and that each city has its own parameter, the aging rate, the proportion of men to women, boys to girls, old age to young people, influx of people from other city, outflow to other city. You have different parameters, right? Well, so now, if this is your project, okay, and you're not writing a textbook, it's not a pedagogical tool anymore. It becomes a prototyping tool, right? It's a prototyping tool for presenting your concept, for representing what your algorithm or application or what your innovative solution is going to do. You can say something like, right now with the current system of healthcare delivery, you can only satisfy this level of growth or aging parameter, but with your different model, you can optimize so that you can actually handle more patients, handle more aging parameters. Okay, people age quicker. What I mean by people aging quicker is that the composition of people in your cities becomes more influx with old people and outflow of young people. You know, basically your city becoming Florida. Okay, so you can do this. You can say, what happened if your city right now is becoming more like Florida? More old people move in, young people move out, or they run into accident and then they eliminate themselves from the population. Okay, so oops. So this allows you to, okay, What was I trying to do earlier? Oh yeah, I was trying to do say move the correlation parameter. So this is the picture. Okay, so now it's negatively correlated. When one asset goes up, the other one goes down. But if I make it positively correlated, why is it not updated? I think I started too many kernels, so it's taking a while. Anyway, it's gonna turn to the right, so we'll come back to that answer. Okay. A good example is recently. Now, I don't know if any of you got to watch the video that I sent this morning. Okay, we have this thing called differential equation. Okay, so let me write this in text. Okay, so you have differential calculus. Give me position. This will give you speed. Okay, and you have integral calculus. Give me speed. Record. This will give you total distance. Okay, cumulative. Something like that, right? But think about it. These are kind of like operation, right? Okay, it's kind of operation. Okay. Now, what if I want to make a statement? I can also make a statement. Okay, that relates rate of change with position, right? So this kind of thing where you have something like speed is related to position, and that can happen, right? Because your speed is governed by how far you are. For example, if you're on a highway, you can be faster. If you are in a city, you can be slower, right? Or something like that. So you can have some, you can say that even though speed is derived from change in position, you can also describe the motion as the relationship between things like speed and position. And that, in a sense, is called differential equation. Differential, and that's the video that I sent you this morning. Okay, now differential equation is a little bit more difficult, and in fact, you know, would not be covered by Chris or your year one calculus. It's more important for engineers, you know, financial engineers as well as physical, mechanical engineers. Okay, because they deal with rate of changes all the time. Financial engineers also deal with rate of change. So you have differential equations, okay? Some tough, some not so tough. You know, there'll be plenty of examples for that if you're interested, okay? But I'm not going to talk about it in details. What I'm going to do, however, is show you an example, and this is from something I did, you know, early on, very early on last year. This was when COVID just came out. Right now, COVID, think about it. COVID is a contagious disease, and it's a number game. Let's say one person infects 2 every 3 days. Okay, then that 2 persons infects another 4, 2 each, every other 3 days, right? Another 3 days, and so forth. You can think of it this way. So you can see why it has this kind of exponential growth. And when you hear it in the news, okay, when you hear it in the news, okay, that the pandemic is growing exponentially, that's what's happening, right? Now, obviously, you cannot have infinite case of infection. At the end of the day, you know, at some point you have to stop, right? Because you cannot infect more than 7 billion people, period. Because there are 7 billion people on Earth. So that's like a maximum number infection. Okay, maximum number of infection is 7 billion worldwide. Well, it turns out that you have this relationship of contagion, but of course, you know, you assuming that one person infect two person infect four, you know, and they all keep infecting two each every 3 days. But actually, if one person infect two persons, but the first person dies, okay, or becomes cured, okay, before getting to infect the other person, then this kind of exponential growth will be tampered. Okay? So there is a rate of contagion. There's also rate of death. There's also rate of being cured, recovery. So long ago, mathematicians modeled this as SIR model. Okay, SIR model. So SIR model is basically, okay, let me just do this quickly. Okay, so this is exponential contagion. Oops. I haven't used this software for a while, but anyway, I just want to show you that how it's done. So there's actually three processes. There's S. Well, first of all, let me do this. Let me start with I. I is the infection. I is the infection. R is the recovery. D is the death. And S is the total number existing right now, total case, active case. So you can see that this is what differential equation does. Okay. Now I'm just going to show you one line. Okay. Rate of infection depends on the current amount of people being infected. See that? So this is why the rate of change of something is related to that something, because the more people you have to begin with, infected to begin with, the faster it grows, right? Because the number of changes of cases per day is also proportional to how many you have already, and so A is infection. Okay. Now infectious rate, I mentioned earlier. Forget this. It's just coefficient. Infectious rate is also a matter of how much you have. Oh, sorry. This is I was talking about infection, so I should talk about this line. Okay. The increase in infection per day, okay, is proportional on the current, you know, amount of people who can infect you, but also it is negatively related to this guy. Where's this guy? Sorry. Okay, to this thing. Now, what is this? This is the rate of infection, the number of infection. Now, the number of infection, how can the number of infection lowers the number of infection? Because the coefficient that it multiplies to is the rate of recovery, right? So yeah, you can get more infected if you have more people who are infected, but it's not everybody who is infected, because some of them recovers, and this is the R, this is the recover. Some of them die. So you have this negative influence. So you have positive influence, but you also have negative influence. Negative influence from people dying and people recovering. So now, well, just to make a long story short, you get to something called, let me just draw a picture. In fact, I made a picture a long time ago when the pandemics was just starting. Documents, Mathematica, pedagogical, COVID, yeah. So this was a picture of COVID models in July last year. Yeah, exactly last year. So this is actually what we did, what I did on Mathematica. So imagine that I wanted to do this as a software. So I'm not using it as a teaching tool, okay? In fact, I wrote this as a teaching tool, but imagine that I want to sell this to to the Ministry of Health or something like that, or publish it online so people can play with it. And in fact, I did. Okay, what I did was actually take the data from, what's the source of data? Let me expand this picture. I used the data source from I think Our World in Data or something like that. Our World in Data. Okay, not World Info, but Our World in Data, which is very good. I download the data, then I calibrate the starting position, and this is basically what I predicted from the first wave. Okay, predicted, and in fact, it was very accurate. You know, the total case tapered to around 3,000. It was really accurate up to, say, before we have the second wave. So once we have the second wave, this whole thing goes out the window because this is only calibrated for the first rate of infection, right? So this was very accurate up to, I don't know, October or this November. When we have a second wave, we have to recalibrate, and I just couldn't be bothered at that time because, well, for one thing, the data source they changed they changed the format, I think, a little bit, and I just didn't feel like rewriting the data handling code. Okay, so I just forced it at that, and I just left it, and I would just be using it for teaching. But of course, if you were to do this professionally as a tool to calibrate for the second wave, for the third wave, you know, you would have to make sure your data source is stable, the same kind of format and that sort of thing, and then recalibrate. But you can certainly do this. So this is a very nice thing. The reason why it's very nice is because in the old days, if you want to prototype or pitch an idea of what an application can do, then you have a static picture, just like the one that I showed you earlier. Okay, but now, because this is not just a picture of what the software could do, it is actually a software, albeit very slow software. It's not, you know, it's not running very fast because it's not implemented on C or C++. But it's, so it's quite slow. But you can certainly say, well, what happened now? Okay, like here in this case, what happened when the correlation goes up? What happened when the infection rate goes up? What happened when you have a second wave? You have to recalibrate the whole thing. Okay, then you can make the software compute on the fly as you're demonstrating. So I think this tool, especially with this manipulate, is extremely powerful because it's giving you ability. Okay, it's giving me the ability to teach models intuitively because you can adjust the parameter. You only get intuitive understanding of how a function or how a model works if you can play with it. And by playing with it, I mean trying different sets of parameters, different sets of input. And that's what this thing does. Yeah, this kind of interactivity allows you. So this is what interactive mathematics on Mathematica allows me to do as a teacher of models. But for you as developer or prototyper of innovation, of innovative concept, of innovative application, you would use the same kind of tool, exactly, but not to write an interactive textbook, but to write an interactive demo. Okay, so gone are the days where you would pitch your idea with PowerPoint. Okay, you can certainly make this look like a PowerPoint if you like. Okay, so you can view it like a slideshow. Okay, so you can do this. You can certainly make it a slideshow, and you go to the next page and so forth. You know, whatever. Okay. The point is that instead of having a static slideshow that just has a captured picture, or maybe a GIF, you know, a GIF is a pre-animated movie, but you can't do anything. Your client cannot say, well, what if I change this parameter? What would happen? Okay. Now with this, you can literally, you know, on the fly, change your parameter on the presentation. So that's a sort of tool that I want you to equip yourself with. There are many tools that, you know, I just started the kernel just to show. For example, this is my motivation on what data analytics is. You know, you're modeling a regression, And what you want to do is set the parameter, and the parameter has to be so close to this and so forth. So this is kind of like a tool. This kind of error rate, this is kind of error function. Okay, so fitting the data. What is the fitting the data? What's fitting the data? Is drawing a line that is closest to all the points. So if I have a function that measure, remember last 2 days ago, I was talking about a function that is the distance to your happy place, and you want to minimize that, right? Well, now I don't have a function that minimizes distance to happy place. I want a function that minimizes, function that represents the distance between the line that I draw to the points. So basically, this line is no good, this line is better, this line is no good, and so forth. So if I have a bunch of points, okay, I can create a function that represents not the distance to happy place, but distance between the line. Oops. I think I started too many kernel. Let me just turn everything off and start again. Okay, the distance between, okay, so I have a whole bunch of points, okay, and if I draw a line that looks like this, it's not very good. But if I draw a line that looks like this, the vertical distance, the distance is minimized. Okay. So you can think of a function that represents the distance to accuracy. Perfect accuracy is not possible because there's some, randomness here and there. But let's say perfect accuracy would be something like 95%, as close as you get. So this is very close. Okay. So once again, what do you do when you have some situation where you want to minimize? You go to calculus. So even in data analytics, okay, where you want to fit some kind of data, you want to create a model, you want to fit the data, when you want to fit the regression, some of you may actually have learned linear regression, which is fitting linear line. Okay, so you can't fit arbitrary types, but you can fit this line. So this is called linear regression. Some of you have learned this in high school. Well, you might not know this, but the formula you used in high school to do this was derived from calculus, because the person who did this, okay, created a distance function between points and line, and then minimize this. Okay, so it becomes a calculus, it becomes a differential calculus. Now, the same concept will be exactly what drives modern machine learning algorithm. Okay, except the function is a lot more difficult. Instead of having a function that represents a line, it's a function that represents classification of pictures. Okay, and instead of having a distance between point to a line, it's some kind of like error rate. Okay, between, you say it's a cat, and is it a cat? Okay, or is it a dog? So a model has to say, this is a picture of a dog, this is a picture of a cat, this is a picture of a mouse, this is a picture of a lion. And then you have the real truth. This is what the model say. So this is the real truth. This is the picture. And this is what the classification. Okay, and there's an error. That error is 0 and 1. In other words, 1 being false, 0 being true or correct. Okay, so it's correct or incorrect, and you want to minimize this. Okay, so inside that app in your iPhone that calculates or predicts cats and dog and picture and do eyes, what's called, there's the eye tracking. So this is part of the picture that represents human eyes. This is a part of the picture that do not represent eye. So let's focus on this part of the picture because they represent eye. Well, whether or not it's the eye, it's the same thing as whether or not it's the cat or there is a cat. Okay, and that function has error, and that error function can be minimized with calculus. Okay. So ultimately it's everywhere. Now, what I should like to do, okay, what I should like to do is, hold on, let me see what else. This is quantum computing. Okay, you might have that in. By the way, have you ever heard of quantum computing? Anybody? Yeah. Well, quantum computing. Well, if you know anything about computers, okay, the first thing they say is computer represent everything in zeros and one. Okay. Well, in quantum computing, you represent something that could be in between 0 and 1 up to a certain point. Then it's like a spinning coin. Okay, it's not 0, it's not 1. It's some kind of probabilistic state. Okay, now a spinning coin is 50% 0, 50% 1. Okay, but a quantum computer, you can tune that probability, and in fact, you can represent your problem as probability of zeros and one, just as you can represent any calculation in a classical computer as series of 0 and 1. Well, in quantum computing, you represent your solution in terms of zeros and 1, but your calculation comes from tuning that probability of 0 and 1. And guess what? How many 1, how many 0 do you have? You have lots of them, right? So how do you deal with lots of variable? Vector. Okay, so in fact, you would see that, well, this is from my quantum computing code. Okay, you would see that, yeah. So this is a normal computer has 0 and 1. Okay, except instead of drawing it horizontally, I would draw it as a vector. So that's it. So zeros and 1 in computer is a vector. Now, with computers, with normal computer, it can only be 0 and 1. With quantum computer, things can be in between. And that's why you have this kind of intermediate. And this is an example of quantum computation. Okay? So quantum computer is based on something like this. It's based on matrix algebra, matrix multiplication. Now, of course, of course, this is multiplying 1, 2, 3, 4 numbers, right? In real life, yeah, you never have something like a likewise here you have 4 number. In real life, you don't have a 4-bit or anything. You have gazillion bit. Okay. Well, right now, by the way, state of the art, I think worldwide, we have quantum computer that has about 5 bits that you can play with. Okay, I think the state of art is something like 49 bits, but that's not available publicly. There is a sort of like a quantum computer that is made available for you to play with online, and I have played with that actually. I played that way back when this thing was starting, 2018. A real quantum computer, except it only had, I think, like 5 bits that you can play with. It was sponsored by IBM, and through some kind of portal, I could execute a code. Well, basically just a GUI, create a quantum algorithm. Yeah, but very primitive, something like, finding a number between 1 and 4, something like that. Okay, so quantum computer is driven by linear algebra. Financial analysis here has linear algebra in here, but because you're not just trying to find return and risk of a portfolio, you're trying to minimize the risk, maximize return. Now you use not only linear algebra here, you use calculus over here. Okay, so you want to find like a lowest risk, so you want to go down here. So you can see why. Well, this is drawn on the flip side. Oops, sorry. Look at this picture. Look at this picture. Now, this is by convention what financial analysts look at. It's pictured like this. But from your point of view, you've seen this line before, except you've seen it sort of like flipped, right? So instead of this being y and this is x, this is x, this is y. So if you cant your head to the right, you will see that this looks like that function that we drew earlier, distance to happiness. So in financial analysis, instead of finding the minimum distance to happy place, they would find the point of minimum risk. So they would actually go to here. Okay. Now in this problem, the minimum risk is not good enough. They also want to maximize return. So it becomes a sort of like compromise between this point, which is minimum risk, and this point, which is maximum return. And they want to elaborate. They want to go to here. This, by the way, is what supposedly, when you put your money to a asset management firm, they supposedly put your investment along this line. Okay? In theory. In practice, use other techniques and other approach for certain reason of market efficiency and whatnot. Okay, but so in finance you have both linear algebra and matrix. I challenge you. I know you're not going to probably raise any hands here today. By the way, this is last time I didn't show you this picture, but this is intersection of planes, so you get a unique. Okay. So you're not going. I'm not going to ask you to give me a topic of interest right now. For one thing, you're only coming in. You haven't found your area that you want to go into. But 4 years from now, let's say once you graduate from Barsai, whatever your final project will be, okay, whether it's healthcare, sustainability challenges, smart cities, and especially applied digital intelligence, chances are it's going to involve some kind of optimization. Okay. Now, when the problem is low enough dimension, you don't need computer to do that. You don't optimize. I jokingly call it optimal, manually optimize, right? If you have 3 choices and you have to choose between 3, you try all 3 choices and which one is best. Yeah, something like that, if you can try it. But still, it's not all that easy. Think of it this way. Even though you have 3 choices, what if you cannot compute the 3 choice or impact of the 3 choices beforehand and choose? In other words, you don't have that function, right? So the 3 choices is, okay, turn Bangkok into city of one-way street. 2, make all intersection in Bangkok a roundabout, no traffic light. 3, leave it as is. Okay, those are the 3 choices, right? So you would think you don't need calculus because you don't need this. You don't have this function. You just have 3 choices, A, B, or C. The point is, you only have information on one choice, C, current state of traffic. You don't know what happened to traffic in Bangkok if you turn all the stoplights into roundabout. You don't know what would happen to traffic in Bangkok if you turn every street into a one-way street or any kind of combination. So you have to simulate. And simulate means you have to play with simulated system. And how do simulated system move? It moves according to, you guessed it, differential equation or something like that. Okay, something like that. Some roundabout way of thinking. Okay, so you really can't get away from this. Now, chances are you're not going to be programming all this thing yourself, right? But you have to understand the technology, the limitation. You have to know that, okay, this model is linear. It cannot incorporate non-linear assumption. Okay? And that's the level of analytical literacy we expect from Barsai students. Again, even engineers these days don't program everything from scratch. They use library. But the library of algorithm has so many knobs and things to tune and adjust and change. So you really need to know how it works. It's like you're an auto mechanic. You don't create the engine. But in order to work on it, you have to know what different parameter does. different, you know, camshaft profile. What does it do to the horsepower and whatnot? So you need to know what you're doing. Well, you are level above that because you're not the car mechanics. But let's say you are a race director. You want to say, I want to work for this race car to be optimized for torque or for traction or for acceleration or straight line speed and this and that. And you have to know that the mechanics or the underlying models that drives all this performance figure is driven by this aspect of mathematics, this aspect of mathematics, and these are the assumptions of the model, these are the limitations of the model. So you have to work with your engineer. But you can't just say something like, okay, you're my race engineer, make this car faster. Okay. Okay. If you do that, you're not a race director. You can't just say something like that. Same here. In the future, a business owner cannot just say, okay, find me a product that sells really well. Okay. So help me find marketing strategy that will get a lot of likes and become very popular and make me very rich in 5 years. It's silly. Okay. It's just a wish list. Okay. Basai student, if you're going to own a business, if you're going to run something, you're not just going to be some guy who sits there and say, I want this, I want that. I want my product to work. I want people to buy it. I want to make a lot of profit from it. Find me a solution. That's not the conversation that you can have with your engineer. That's not a conversation you can have with your marketing director. That's not a conversation you can have with anybody. Okay, it's a baby conversation. It's like, I want the moon. It means nothing. Okay, but if you say, I want to go to the moon, and I understand what the technology set is required to go to the moon. What's the limitation? What kind of additional resource? Is it about propulsion? Is it about flight control, electronics, this and that? Okay, fine. If it's about flight control electronics, I would invest in department that develop flight control electronics. If it's about this and that and so forth. Okay, but you can't just say, I want to go to the moon and leave it to whoever. Okay. So as head of NASA, you can't just say, please find me a solution to go to the moon. You have to know how things work. And that's the sort of literacy, analytical literacy we expect from Basai graduates. Okay. So you're not going to be the nitty-gritty programmer. Although if you can do a lot of programming, like with Mathematica and Python, you can prototype, that's good. You're not going to be the actual engineer who fine-tunes every knobs and every setting, okay? But you are going to be the one who understand the limitation of the technology, understand the mathematics, understand the modeling, the logic, how things work, how things don't work. Why is it that this model picks a face? Why is it that this model recommends a fruit salad to this particular profile of a health patient? You have to understand all this, okay? And this is how you can become innovative. You can say, okay, I need to bring this part to the solution. I need to bring this to the solution. I need more advanced propulsion. I need a way to do rocket guidance when you don't have a big computer on board. That sort of thing. Okay, so that's the sort of analysis that we would expect from Basai to be. Okay. A final word is that some of you may have the feeling that if this is all difficult, okay, I would just go to the easier, the least technical part. But you know, at the end of the day, if you think about it, if all you have is imagination of what the product should look like, okay, and you have somebody else who has the deeper understanding, okay, is your imagination so superior to the guy who understands the mathematics and modeling assumption and all this technical aspect? Is your imagination is going to be so much better that he's going to have to pay you a lot of money for your imagination, right? Chances are, if you can imagine it, so can he or she. Okay, so that's why it's not good enough for you guys to imagine. Okay, in terms of innovation, I think there should be an app that an elderly patient press a button and it will recommend what she should eat that morning. And that is very childish way of thinking. That's very, superficial. It's like wanting to go to the moon. Okay, so you are supposed to communicate to the engineers, to the developers, to the data scientists, okay, to the system analysts, all this in a more intelligible way. Okay? The way that means that you understand the technology, how it works. You don't know how to code it yourself professionally, as neither do I. In fact, I don't do professional coding for my consultancy work. Okay, but I do my prototyping with Mathematica. I have the mathematical formulation. I have the solution. I have all this. Okay, so with that, I think I'm going to take a little break because I want the TA to have some kind of show and tell as well. So he's going to show you, or both of them. Let me turn the screen over. Okay, so I think they work in pair. I was actually hoping for 2 demonstrations, but I think they were working together. So, Petong Kap Kap Kap, are you ready to have a go? Let me turn off my microphone because there's a little bit of construction upstairs, so it's going to give you a lot of noise. So let me turn off my microphone. So you guys, please have a go, and we'll leave. Yeah, just take about 10 minutes, 20 minutes if you like, whatever. Okay.
Thank you, Kapil. Okay, hi everyone. Today I am Pipetong will introduce you all about the basic concept or something you might interesting. So this is about the compound interest and the continuous interest, and you also will see some codes in the Mathematica. Okay, at first, I will use the Excel to make you easier to understand this concept. Okay, let me share my screen. Okay. Okay, to begin, I will briefly talk about the concept of this called compound and continuous interest. So let's imagine that we are on the first day of January or the first day of the year. And we have 100 baht. Okay. And then you can choose to invest this money into like many money instruments, like depositing this money to the bank or like investing in the stocks or like buy Bitcoin, whatever you want. Okay, for example, if I choose to deposit this money into the bank and the bankers told me that I'm gonna get the 10% return each year. Okay, this is my return. Return 10%. Okay, so if I invest this 100 baht at the 1st of January, it means that at the end of the year or like 21st December, I will get my 10% of the 100 baht, right? So I will get, okay, let's move this. I will get 10% of 100 baht, which is equal to 10 baht. So at the end of the year, I will have 110 baht. So this is easy. You all know this. But what if in the second year? So let me, okay. What if in the second year, for example, 22, this is 21, right? So at the beginning, I will have 110 baht from this year, right? This is the same. And at the end of this year, at the 21st December of 2022, I will also get my 10% return as as the first year. So my 10% return multiplied by my my money at the 1st of January is 110, right? So it's gonna be 110 plus 11, and it is equal to 121. Yeah, let's see one more year, okay? About the 1st of Jan in 2023. So at the beginning, we will have 121 baht, right? And at the end of the year, we will get 10% return of 121. So we will have around like 133 baht. This is quite simple, but the thing I want to show you is our return. As you can see, our first year return is 2 of this, right? At the first we have 100, and at the end of the year we have 110. So our return is too much. So our return is 10 baht, right? So then our second year return, we have 121 from 110. So our return is 11 baht. And the third year return, we have 133 from the 121. And this is 12 baht. The thing I want to show you is that our each year return increases every year. As you can see, as this is increased 1 baht, and this also increased in 1 baht, 10, 11, and 12. It's not 10 all the time, but it increases. So this is called the compound interest. This is the simple concept that if you invest the money and you keep it there and wait for the return for each year, this money will grow, but not grow steadily, but it will grow like exponentially. So I hope this is clear for you. And yeah, I will show you one more example, because this example is that you will get the return annually, or the bankers will give the interest to you once a year. But what will happen if you get the return semi-annually? Or it means that you will get return 2 times a year. Okay, I will show you another example. So assume that we get the same return as the previous example, which is 10%, but now you will get it semi-annually. So it doesn't mean that you will get 10% 2 times a year, but in fact this 10% will be divided into 2 times. Okay, so now this is an example for the semi-annually. Our return is the same as okay, sorry. As I told you, this 10% return will be divided into 2 times, right? So if we divide it, if 10 divided by 2, it means that it means that you will get 5% per time. Okay, so let's look at the numerical example. as the same. I will copy this. Sorry, copy only this. Okay, at the 1st of January, you deposit 100 baht to the bank. And then as the banker will give you, give the interest to you 2 times a year. So you will get your first return at the middle of the year, right? So it's going to be like the 1st of July, a half year, right? You will get your 5% return. So it is 5% multiplied 100. So you will get 5 baht, right? So now you will have 105. And then at the end of the year, 31st of December, you will get your another 5% return, right? So the 5%, but your money is 105. So you will multiply by 105. So you will have like 110.25 baht. Okay, and at the second year, you will get your first 5% return at the another at the end of the year as the previous example. But the thing I want to show you about the difference of the annually and semi-annually is that, as you can see, if you invest in the same time, like 1 year, but you can see that red, you will get the different number of your money at the end of the year. And if you get semi-annually return, you will have a higher money at the end of the year. Or in other words, you will get higher return if the bank give you a more frequent of the return. Or like if they give you like quarterly 4 times a year instead of semi-annually, you will get higher than 110.25. Okay, so let's think how many times do you want the bank to give the return to you per year, like 4 times a year or 10 times a year or like 100 times a year. So what about they give you infinite times a year? Infinite time a year. And this concept, this infinite times a year, is the concept of, sorry. No. This is the concept of continuous interest. It's different from the compound interest. The compound interest is that when you know how many times they will give you, but the continuous interest happens when it is infinite time. You don't know how many times. So this is the core concept of the compound and continuous interest. So next, the Pipetong will explain you more details about the compound interest and also the continuous interest, and you will see some code from him. Thank you. Okay, ไปต่อครับ ไปต่อ your microphone.
Sorry. Okay,ครับ. We get the concept of compound interest by Pickup, and we will let's take a formula like this. PV mean principal value that we have in the first year to deposit to the bank, and R mean interest rate that bank gives us. N mean the period time that Pickup told you about semi-annually or annually, or it's 10 times a year, and the X in this meantime, if you deposit for a long time, you will have a final return at high cost, and it's n is mean at the same n period. It show the formula of the compound interest is 1 plus interest over n period, and then power by time multiple by n period, and then multiple by principal value. Okay, that's the formula for compute a final return. But Pickup told you if we have a continuously compound, the form this if we take a limit of n approach to infinity, this formula will become like this. For E is mean E constant in mathematical is equal to 2.71. Okay, I will show you the graph for more understand. If Pickup told we have interest rate 10%. Okay, let me run this graph. If we start, the bank gives us 10% a year. Okay, and if we want more return, we could deposit for many years. You will see the return. A red graph is mean the formula, this formula, but blue graph mean ideal for continuously compound. And if we deposit for many years, like 30 years, you will see we have more return at the end of 30, 35 till 6 years. But if we want to increase a final return, we can increase by take up n time a year. That is a number of interest is compound per year. You will see if we increase n, red graph will become close to a blue graph, but it's about it never go higher than blue graph. But you will see the result final it will more close approach to a blue graph. Okay, let's see clearly if we increase rate to like 50%. Okay, you see it's more different than 10%, but you think you could have a more return than is B, but you can increase a period n, and you see the graph more come close to a blue graph that is continuously compound. But in real life, we cannot have a period n approach to infinity or continuously compound. But you see, if we increase just 1, 2 times, the final return increase. But if 12 times or 30 times is more, not very different to an ideal. Okay, and if we take a period n approach to be 500, it will be this value, but it's never greater than continuously compound. Okay, I think you clearly understand why we can use E constant in a continuously compound and compound interest. โอเคครับโอเคครับอาจารย์ฮัลโหลครับ
Okay, well done. Okay, Kap. Can you go up a little bit? Go up to the code. Okay, Kap. Showน้องๆ that highlight the line that say plot, I think. Yeah, okay. So as you can see, that's really essence of this. The essence of the whole computation is that function. Okay. Now the coding looks a little bit complicated, but if you look at the rest of the items, it has to do with a lot to do with formatting. Okay, so in fact the code is it looks long, it has a lot of words, it has a lot of specification, but a lot of the parameters that are specified here just have to do with formatting. For example, you see that to the right, it says something like, okay, what range are you going to plot it to? Okay, grid line, plot style, ticks and filling, all this are optional, right? So Petong, could you for example just eliminate all the option, just delete all the option and just re-execute. It would also show that the point is that the reason you get a lot of complication here that you see has to do with formatting. So in fact, it's very easy to program, right? That's the point I'm trying to say. So you need two things. You need, first of all, you need the function that you want to exhibit, and second, you need the parameters that you want to manipulate, and that's what this means, manipulate. Okay, so all these things, pane, the word pane, column, text at row, text, all, yeah, exactly. So all this are very important to make it, yeah, to make it professional looking. And in fact, a lot of software engineers spend a lot of time doing this as well. Okay, so there's the key part of the code that does what you want it to do, and there are 70% of the lines of the word of the instruction that has to do with peripheral part. This is what I mean by the difference between professional and people who are articulate in understanding the prototyping or the concept. Okay, so to make it a professional product, you have to do all this kind of formatting. You have to make sure that the parameters that are input are valid and so forth. For example, imagine that this is an application that you are developing and your client can be free to input any kind of assumption like interest rate. Okay, now obviously interest rate has to be positive, right? But as a software engineering exercise, you can't just assume that. Okay, you can't just assume that your client or the user will know what they're doing. So you have to do this kind of like checking. Okay, is the person inputting the number that is valid? Is the interest rate non-negative? Is it unrealistic or something? So you have a whole bunch of checking and formatting and all kind of stuff that makes the problem very technically very cumbersome, and you have to do a lot of stuff. But if you understand the basic foundation of what you want to do, basically that line, you want to plot the exponential function for over a range of x. That's the level of conversation I expect Basai students to be able to communicate with, say, professional coder, professional software engineers. Okay. So anyway, that's very good. That's very good. Let's see, where are we? Normally I should like to really have a good conversation with students in terms of what they're looking forward. And in fact, in most of my class, I would prefer to have a direct interaction so I get immediate feedback. So for example, certain things about the presentation on Wednesday morning, if I knew that there's some issue that you want clarified, and that's brought to my attention right away, then certainly I can adjust the material, adjust my plan, and so forth. But right now, I sympathize with you guys, the fact that we can't do a lot of interaction, and most of you are a little bit too shy to raise your hand and ask for questions. So that's why a lot of the teaching or communication has been one way. Okay, so that's not what I like to see. So that's fine. I mean, it's not that consequential now because it's just a pre-course. But as you go to the next class, when you go to your proper class in fall, in autumn, I don't want you to be this passive. Okay, it's for your own good. It's much better for you to if you get lost, say by the second class, and just leave it to the end, and then you just very sad about it, and maybe you give the feedback to the teacher that say, something simple like, okay, could you speak slower? Okay, now if you said that in class 1, maybe I could have slowed down my speaking or my pace. But if you don't say anything and you sleep to the end, and then maybe you give me back the feedback that I couldn't understand because you were speaking so fast, well, it's too late. It's too late. Okay. So again, most of you are probably quite shy, I guess, and whatever, for whatever reason, haven't raised comments or anything. But for the next class, when you begin your class, with Chris, with all the faculties, it's best. It's in your interest, and it helps them. It helps them. It helps Chris. It helps all the teachers to very much fine tune. Okay. So the material, yeah, the material is on the syllabus, but certainly the style, the emphasis on example, the emphasis on function. Some of you may say something like, I understand better with commercial example. Yeah. Some of you may say, I understand better if I get a formal textbook reference or something like that. Okay. Now these are things that are feedback that if you leave it to the end of the class, it's useless, right? It may help the next class, but again, next class may be different kind of population, have different kind of preference. Now you can make all these suggestions, but then ultimately it's up to Chris, it's up to the faculties to fine tune what they want to adjust. They might not be able to adjust to all your syncretic or special preference, because after all, teaching a class means you have to teach a class, the whole class, not just one person. It's not a personal tutorial. But I would encourage you to be more interactive. Okay, try to be more interactive. If you don't want to raise your hand and speak out, you certainly can use the line chat. Oh, sorry, the Zoom chat. Right now, in each class, the teacher would monitor, or maybe the TA would monitor. Okay, or somebody can help. Somebody who's not more vocal can say, "Oh, teacher, there's a question from the floor," or something like that. Okay? So I really would encourage that. I would encourage that. I think now I'm not leveling this criticism to you guys, but sometimes I see students, or maybe new generation, and this I could be wrong, having a wrong kind of activism. When it's time and place where we ask for your opinion or ask for feedback or something, so you can be more interactive. Sometimes the student would just be silent, and then they'll go to, let's say, not this class, let's say, go to a Facebook or a line group and complain about it. So that's kind of like being active in the wrong place. Okay. It's saying, oh, the system doesn't work for me. This is no good. This sucks. I don't like the way my parent does this. I don't like the way school do this and that. But when there's way to be creatively engaged, a lot of times students are silent. So I would encourage students to be the opposite, creatively interactive and engaged. Okay? It's easy to be passive and then complain. It's much better to not be passive from the beginning, okay, and be engaged. Okay? Then you will have, the downside is that you have no reason to complain at the end because you partook in the process. Okay? But that's exactly what a creative learning environment is. Creative environment is not, coming to class with a certain expectation, and you get something, and at the end of the class, you either like the class or don't like the class, or like the instructor, or like the homework, or like this, and or complain or whatever. That's not interactive. That's not creative learning. Creative learning means you actively take part in the learning process. So I really hope that for one thing, you guys are actively engaged in the learning process, and I hope that that you're not just being shy or because you don't like Zoom. Once you get used to Zoom is or Zoom or Team or any kind of online platform. It's going to be a normal part of life. It's part of your generation. Okay, so you have to learn to be interactive with your instructor on this medium. Yeah. Likewise, teachers have to do that as well. Yeah. For example, there's a good guy. There's a guy who raised a hand. Shinabu. Yeah. Go ahead, please. That's good. Hello.
Ajahn, can you
Yeah,
give
good.
an overview of what knowledge and basic you need for applying for artificial intelligence in year 2 for Basai?
Okay. Very good. Like I mentioned, artificial intelligence. Well, there's a whole lecture that I have to give, but basically, if you think about it, artificial intelligence. What's the aim of artificial intelligence? It's to capture human intelligence, but without the human limitation. Okay, think about it. So it's not going to do stupid computation. It's going to do intelligent computation like a human mind, but it's not going to be restricted by the human mind's capacity. Okay, so the whole thing about artificial intelligence, if you think about it, right? Okay, there are many schools, there are many things, and different paradigm. I can go over that later. Of course, I will in my class. You have to understand that at the end of the day, artificial intelligence is only useful because it does what human does, only without the limit of human capacity. In particular, for memory. Because we can only remember 5 items at a time, but computer can remember 5,000. We can do 2 calculations in our head, computer can do 5,000 calculations in our head. So the first thing you have to realize is that the mathematics that will be required for artificial intelligence is the mathematics that allows you to deal with bigger amount of data, higher dimension. And what have we been talking in this class that allows you to do that? Deal with multiple things at the same time? Vectors, right? So think about that. So your computation, human being, you can do computation on 2 or 3 things. If you put 2 or 3 things in vector form, and you tell the computer to do computation on vector, except when you give the vector to computer, you don't give it 2-dimensional vector like you would do. You would give the computer 3,000 dimensional attribute. So linear algebra is, I would say, number one. Linear algebra is number 1 requirement. If you don't have linear algebra, forget about machine learning, forget about artificial intelligence, forget about optimization. So linear algebra is the most important thing. That thing that I mentioned earlier about say eigenvector, eigensystem, that will show up, that will come up. Okay, there's a lot of things that has to do with reducing the dimension. So now we were talking about multiplying a vector by a square matrix, so you end up with the same dimension. Well, in machine learning, this becomes more fluid. You may start with 10,000 dimension. You multiply by some matrix and you end up with 50 dimension, and then maybe you multiply back again to 10,000 dimension. So the dimensionality is very fluid. Okay, it's very fluid concept. In deep learning, you can think of deep learning. Now I'm being a little bit untrue here, but you can think of deep learning as one of the elements of deep learning is you just multiplying matrices. Deep means deep. in this sense, the word deep corresponds to not just one matrix, but many matrices in sequence. So it's deep in that sense. Okay? Think of a hole, right? You go down one level, that's not deep. You go down 2 levels, that's deeper. Okay. Well, think of matrix multiplication as one layer or one level. Okay. Deep learning is like many matrices multiplication. Okay. There's more thing to it, obviously. Okay. So the first thing is linear algebra. Second thing, in your artificial intelligence, if you think about it, artificial intelligence, you're not trying to create a free form intelligence, something that does some kind of new behavior that doesn't have any link, any connection with real life. So at some point, even though you talk about artificial intelligence, at some point you have to calibrate the behavior of that artificial intelligence to real data. So at some point you have to match what the AI does with real number, with real data. So at some point there's going to be quote unquote reality check. So every time you have a reality check, mathematically it's equivalent to an error function, right? Because reality check means you have to check reality versus model. Okay, if the model is giving nonsense, it's not realistic. So reality check will come down at the end of the day to some kind of error function. And if you want the model or AI to be realistic, you want that error to be small. When you want something to be small as possible, you are minimizing. When you are minimizing, you are using differential calculus. Okay? So, you know, I could have answered your question in a very simple form. What do you need for machine learning or artificial intelligence? Linear algebra and differential calculus. Okay? But I gave you a long narrative, so you understand that this is not just because, you know, linear algebra and calculus is taught in the first year. Linear algebra and calculus is taught in the first year precisely because so many subjects, architecture, design, urban planning, pandemic modeling, biological process, all kind of stuff uses this. And in that case, machine learning, artificial intelligence is no different. It's no different. Okay, so it's not a very, it's a, you know, basically, yeah, lots of matrix algebra, linear algebra, multiplying with matrices and so forth, and minimization. In particular, minimizing error. Okay, you can be more creative. Okay, you can maximize certain things. For example, maximize profit, maximize, you know. So at the end of the day, it comes down to this optimization. And again, optimization is done by calculus, right? Good thing is, for artificial intelligence, you would need to know a lot more about linear algebra than calculus, because sometimes once you get to the stage where you formulate your problem as error minimization, there are some standard procedure to minimize that error. So you don't need to sort of like configure the error minimization to suit your problem so much. But if you're going to be an innovator, you definitely have to work with the architecture, with the configuration of, do we put this kind of matrix or that matrix? So linear algebra is a lot more, it's going to be a lot more of a must. They both are a must, but definitely linear algebra. Okay, so if you're going to machine learning and algebra, artificial intelligence, if you get A in linear algebra and C in calculus, you can get by. But if you get C in linear algebra and A in calculus, you won't get by. Okay, I'm just being general here. Okay, very good. That's good. I like that. Okay, and again, do this, but do it early in the early classes. and that would benefit both the instructor of the course and also, you know, whatever improvement the course end up with, it's going to benefit your next peer, your friends, your youngest. Okay. Okay, so with that, I think we come to the close. We've gone a little bit over time, but you're doing very well. I will send you the link to next Friday's introduction to applied digital intelligence track. Actually, you will have links, I think, to all 4 lectures, right? Smart cities, the health, healthcare, health science, health service, the sustainability challenges, and applied digital intelligence. So you have that. But I think, yeah, applied digital intelligence is next Friday, I'm pretty sure. Okay, so it begins with this. And some of you may be interested in applied digital intelligence because you are interested in applied digital intelligence. Some of you may be interested in this track because you actually want to solve smart city problem, but the technology to do that is going to be heavily focused on using digital intelligence. So in which case you might do 2 things. You might say focus on the smart city as your concentration, and then the applied digital intelligence is the tool. Or you can focus on applied digital intelligence as your major track, and then think of smart city as an application area. Okay, it works both ways. Okay, Kap, with that, I think we are well and ready to you know, I'm well and ready to wish you well onto a journey. Okay, let me just leave one final comment, which is that the next 4 years can be the most exciting intellectual years of your life. Okay, I have a PhD, I have a master, I learned a lot during my PhD, I grew a lot in my professional years because I'm a lifelong learner, but nothing compares to the 4 years, 4 or 5 years, actually 3, 4, 5, because I did my master there as well. So nothing compared to the 3, 4 years right now, where your brain is actually mature enough to be fully competent at abstract thought, but young enough to take in a lot of new material and not be exhausted. So use it well. Okay, don't waste it on nonsense, on silly, I don't know, soap operas or I don't know what silly things you have. Okay, but you have precious brain for the next 3 or 4 years. Okay, use it wisely. Okay, use it wisely as a base for the rest of your life. So I wish you well. It's a journey. It's a journey. Every year will be different, and I wish you all the best. And I will see you guys. Some of you in my track, some of you occasionally, but I wish you all the best. Okay, nakap. So with that, so I think we should come to a close. Thank you for everyone for your attention, and the TA, you did a good job today. This is the first time, okay, that I challenged you to do something like this, and you did a good job, both of you. Excellent. Okay, well done. Okay, Kap Pinat Gongkan, who's going to be my TA for the more advanced class, I thank you as well. He's very helpful. All the students love him because he's very helpful, very courteous, and very patient. Okay, he also explains things a little bit slower than I do as well. Okay, so good luck to everyone, and I'll see you in autumn. Okay, Kap.